See this structure? Looks scary and devoid of any possibility of life. But this is our home, the Earth, at the beginning of its existence 4.6 billion years ago. And its formation and the formation of the Moon remains a mystery. But today, we'll tell you about the theories that scientists suggested. You'll learn how planets so different from each other form from the same material, what planet crashed into the Earth in the past, how much water there is on our planet, and where it came from. And finally, we'll tell you how old the oldest organism on Earth is. We prepared the story of our planet from a clump of dust and gas a few miles in diameter to the appearance of life. When the Sun was created, gases and other materials around it started colliding with each other and forming small bodies called planetesimals. And as the gravitational forces were growing, more material was pulled together, and these seeds of planets grew larger until they became true planets. The solar system's gas giants, Jupiter and Saturn, Uranus and Neptune, were born much earlier than the 4 known terrestrial planets, Mercury, Venus, Earth and Mars. But how exactly was our home planet born? The Earth's story started about 4.6 billion years ago in a disc-shaped cloud of dust and gas rotating around the early Sun. And we know it was that long ago because of the fossil record, one of the most simple methods to determine the age of our planet. Scientists were able to find zircon crystals that are roughly 4.3 billion years old. So far, these crystals are the oldest materials found on our planet. But how exactly our planet was formed remains a scientific mystery. However, there are 2 leading theories on planetary formation. The core accretion model is the first one, and most widely accepted. About 4.6 billion years ago, there was a solar nebula consisting of spinning gas and dust particles from which our Sun was born. Then, as the remaining material of different sizes orbited our star at slightly different speeds, it started to collide and stick together. Under the effect of gravity, smaller particles grew into larger particles that ranged from miles to hundreds of miles in diameter. The solar wind would then sweep away lighter elements, such as hydrogen and helium, so that just rocky materials would stay closer and turn into terrestrial worlds. The process continues until these space objects reach thousands of miles in diameter. But far away from the star, the Sun's constant stream of charged particles doesn't have a very strong impact on lighter elements. As a result, these elements combine and transform into gas giants. What's exciting is that NASA believes that this is the way planetary formation works. Small, rocky worlds like the Earth are a lot more common throughout the universe than gas giants. The thing with this theory is that it works well to explain the formation of terrestrial planets, but has problems explaining the creation of giant worlds. This is because scientists believe the gas disk around our Sun only lasted about 4 to 5 million years, and simulations based on the core accretion model show such planets form longer than that. However, the second theory, or the disk instability model, resolves this issue. This newer idea suggests that chunks of dust and gas clump together early in the existence of the solar system, and over time, these chunks slowly turn into a gas planet. But the difference is that this way, planets can form much faster than those explained by the core accretion model. In fact, according to this theory, it could happen within as little as 1,000 years. A planetary formation this fast makes it possible for such worlds to trap the rapidly vanishing lighter gases. A recent study suggests that Proto-Earth was formed within about 5 million years, and on a cosmic scale, it's nothing. If we converted the solar system's estimated 4.6 billion years of existence into a 24-hour period, these 5 million years would be equal to just about 1.5 minutes. If scientists are right about this, water could be just a byproduct of the formation of a planet similar to our home. This would mean that we're a lot more likely to discover the ingredients of our life outside our solar system.